Good morning, friends. In chapter number 1, today we are going to see overview of advanced machining processes. That means in this lecture we are going to discuss working principles of some of advanced machining processes. Now let us take some example of events which we see in our everyday life. Now here in this particular figure, and this is very interesting. Now here if you see this particular figure, water is coming from the tap, and all of you have a tap at your home, and the water is coming, correct? And if you put the wooden piece under the tap, you will find that after few days a crater has been formed. Okay, so now the question arises, how water is able to cut the wood? Because we have just studied that tool material should be harder than the workpiece material. There is nothing like a tool, only water is coming falling on the wood, and still it is able to create a crater over here. Or if you, in place of wood, if you place a lump of soil, okay, you will find that this crater is bigger than the crater that has been formed on the wood. Okay, now the question arises, how water is able to remove the material from the wood or soil. So keeping this in view, this destructive feature, in some sense, I just ask a question to all of you. Could you think to make use of this destructive phenomena in some constructive purposes? For some constructive purposes, people took the inspiration from this phenomena and they developed a process which is known as water jet machining process. Same way, in rainy season, if you see that water coming out of the tap, you will find that some sand particles are there mixed with this water, and as shown over here also. Now when this same particle along with the water jet, they come and hit the stone, you will find after a few months or few days, crater has been formed on the stone also. Now the question arises, how this jet of water and few sand particles is able to remove material from the workpiece as hard as stone, or if you place or replace this stone by alumina, you will find much bigger crater has been formed on the aluminum. So what I mean to say here is that, can you make use of this destructive phenomena for some constructive purposes? People have taken inspiration from such phenomena which they saw in their daily life, and they developed the process what is known as abrasive water jet machining process. Okay, here sand means the your abrasive particles. Okay, and from that you can remove the material from the stone or aluminum. So now there is the third process also. If you see here, here is the jet of air and abrasive particles coming out of the nozzle. Now when this jet comes and hits the stone or brittle hard material, you will find a crater has been formed over there. Okay, now when this jet comes and hits the stone, you will find the crater has been formed. In place of this stone, if you place the aluminum, you will get the much bigger crater has been formed compared to the what was formed on the stone. Now such kind of destructive phenomena have been utilized for evolving and developing the machining processes, where very delicate sophisticated machining processes which we are going to discuss in this course. Okay, and this the combination of air and abrasive particle, if you use it, is called the abrasive jet machining. Now how does it work? Here kinetic energy of water and abrasive particles make it possible to remove the material, and the velocity of the abrasive water jet, it is as high as 900 meter per second we are using. Okay, now there is another process called electric discharge machining. Let us see how it evolved. There were two brothers, so I am going to discuss the history also here. Lazar Lazarenko brothers in the old USSR, and one day they found that male and female parts of their switches, they were having the dark metal, dark spot over there, like this. Okay, if you see here, and some material have been removed from the male as well as the female parts, and both of them started thinking how to make use of this destructive phenomena of a sparking for some constructive purposes. They kept trying for years together and developed many machines, but none of them worked. Finally, after a long time, they were able to develop a machine which they named as electro spark machining, and today it is known as electric discharge machining. And they patented it, and the working principle is very simple. You have a tool over there, and you have the workpiece in between the, okay, and in between this tool and workpiece you flow what is known as dielectric fluid, and you connect this tool and workpiece to the pulsed DC power supply, and when the potential gradient between the two electrode is more than the breakdown voltage of the dielectric, then a plasma column is formed between the two electrode, and sparking takes place, and because of that sparks the material is removed from the tool as well as the workpiece, and finally you get the shape of the cavity on the workpiece, which is very close to the shape of the tool. But mind it, here material is being removed from the tool as well as workpiece, but we want to material should not be removed from the tool, it should be removed from the workpiece only. Okay, now there is another interesting process or thing which in our childhood, in their child age or young age, they keep doing this magic. They take they take a lens, they concentrate on a paper, they concentrate the sun rays on the paper or piece of the paper, and they burn, and they enjoy this burning of the piece of paper, and they call it a magic. Similar kind of concept has been utilized. If you see here, in case of laser beam machining, you are doing the laser beam machining, you are concentrating the laser light way at a very small spot on the workpiece to be machined, or to be given a particular shape and size, and the heat intensity of this laser light is so high that you can melt or vaporize any material known to you. Okay, and the you concentrate here laser beam and very small spot, and temperature goes to very high value, and you can machine or you can melt and vaporize, you can get the desired shape and size on that workpiece. So now there are certain problem with some, there are the certain problems with the some materials which got high thermal conductivity, high thermal conductivity and high reflectivity. They can be machined, but performance of the process become very poor, especially in case of aluminum, copper. So very low machining efficiency using this particular process. In the beginning, at very low machining efficiency. Machining efficiency was low as less than 1%. Okay, so this is about the laser beam machining. Now let us see the working principle of some other advanced machining process. Now there is another advanced machining process called ultrasonic machining. Now in this ultrasonic machining, here you have the tool which is vibrating at ultrasonic frequency, that means near or more than 20,000 hertz, means 20,000 times per second. It is vibrating with the certain amplitude of vibration, and here if you see here there is a slurry which consists of a liquid, say water, and abrasive particle. And when the tool hurts a particular abrasive particles, it comes and strike with the workpiece. Say here ceramic is the workpiece material, and so 1,000 times of abrasive particle are hit by the tool, and they come and strike the ceramic or the workpiece material, and they remove very fine crater, or they create very fine crater on the workpiece, and they keep removing the material, and finally you get the shape of the crater form on the workpiece very close to the shape of the tool. And this is used for or machining brittle or fragile materials. Okay, so this is ultrasonic machining. Now there is another process called, this is a plasma arc machining. So you can see here, now in this particular process you see here you have a gas which is coming in, and it is connected to the electrode which is connected to the negative terminal, and here is the workpiece which is connected to the particular positive terminal of the DC supply, and very high potential is applied. And when this gas comes, then arc is formed, and the gas gets ionized and plasma is formed, and this plasma has very high heat density, heat intensity, and you can cut any material that you have. And when we want to cut very thin materials where electrical or electric arc does not work, at that place we use plasma arc for cutting those thick materials, okay, into the pieces. So this is very interesting, very useful process, but this process is used for rub machining or rub cutting, not for finishing or finish cutting. Okay, now this is very interesting process, electron beam machining. I have shown here in this diagram micro holes with the help of uh, here uh, here we have a hot tungsten wire filament, okay, here, or hot tungsten filament which is emitting electrons from the this filament, and here you can see electron gun. Okay, there we'll discuss the all the part later on. And here you have the electron magnetic lens also. Then beam control coil is there, and you can see here this is the electron beam, which is electrons in this particular beam are moving at a velocity which is close to the light. And when such high velocity electrons, although they have got negligible mass, but with such high velocity, half m squared, that is the kinetic energy become so large that they create a very high temperature at the point where they hit the workpiece surface, and the temperature is very high. But the condition is in this particular machining chamber is it should have vacuum. If air is there, then the molecules of the air will stack with the electrons, and they will lose that energy, and you will not get the very fine cut on the workpiece. So mostly the vacuum is created in the chamber, and that vacuum can be 10 raised to power minus 5 millimeter of mercury. However, there are certain versions of this electron beam machining machine where people are using air rather than vacuum, but efficiency is comparatively very low. Okay, this is overview. Now let us focus on focused ion beam. Here, splattering of or knocking of the atoms from the workpiece surface by the kinetic momentum transfer from incident ion to the target atom takes place. I will explain it here with the help of figure. As you can see, this is the ion from some gases coming and hitting the top surface of top surface of workpiece is just sufficient to dissociate one atom from the another top surface of the workpiece, and you can see one ion has separated out one atom from the top surface. But normally the energy of the ion is much more than what you really just needed to remove the one single atom. And if you see here in this particular case, that the ion has much large energy, so in place of one single atom, many atoms are removed from the surface, and the ion gets implanted at the bottom of the below the top surface. And this you can see over here, and this is a way, this is a situation which really do not want in machining, because surface get damaged over here. This is the ideal situation which we want, but normally in practically in between these two situation takes place. At sufficiently high energy, the cascade events will penetrate more deeply into the solid. As you can see over here, several atoms will move implemented deep within the material. That is what you can see over here. So this situation you really do not want. We want this particular situation. So at sufficiently high energy, the cascading event will penetrate more solid several atoms. Okay, so here the removal of material or removal of atoms will occur when the actual energy transferred exceeds the usual binding energy. Okay, Now there is another process known as electrochemical machining. Okay, you must know knowing electroplating. This process is just a reverse of electroplating. In this particular case, you have the tool, you have the workpiece. You have the tool, you have the workpiece. Both are electrical conductive, and then you use what is known as electrolyte. Electrolyte is nothing but the solution of the normal salt in water. There are other electrolyte also, which we'll discuss later on. And when this electrolyte is flowing in between this gap, you connect this tool to the negative terminal, and workpiece to the positive terminal. Then current start flowing in this gap. This gap is known as electrode gap. And when this current is starting flowing, electrochemical reaction takes place, and as a result of that, material is removed from the workpiece, and you get the cavity from the in the workpiece is, and which is close to the shape of the tool. And in this way you can machine any hard material. Now it is a chemical property, metallurgical property of the workpiece which affect the performance of the process rather than the mechanic property of the workpiece. That is, the hardness is no more barrel in this kind of process as we find in case of conventional. And there is another process called chemical machining process. In this process you use the etchant which reacts chemically with the workpiece surface, and you can use the maskant to hide the surface from where you do not want to remove the metal, and you immerse the workpiece in the etchant which is already has a mask. And once you immerse immerse it for the definite period of time, the material start dissolving chemically, and after a certain period of time you take out the workpiece, and you will find the desired shape and size on the component. Okay, so this is a basic principle of chemical machining. So this is a reference from where I have taken the data. Thank you. This is about the overview.